So with that, I want to bring on Bob Sorensen, the Chief Analyst for Quantum Computing at Hyperion Research, and Dr. Bob Sutor, CEO and founder of Sutor Group Intelligence and Advisory. I've known both of these folks for years, Bob Sorensen for probably decades, if we were really tracking years. So let's just say years. Probably quite a long time there. So very happy to have Bob and Bob on this session for our Q&A. So Bob's, thanks for joining.
Thanks for the opportunity, Jay.
Happy to be here.
Well, first, I want to ask you both to just a real quick introduction about your interest in quantum computing and your role in the field. But I also want to make sure that Bob gets credit for this awesome book. It is a tome. It is a real book about quantum computing. It's called Dancing with Qubits. It's on version 2. It's highly recommended. So I'm going to do the plug for you, Bob, so you don't have to do any shameless plugs. And now I'm going to ask you just to introduce yourselves real quickly.
Well, I'll send you $1 for that. Thank you, James.
Oh, $1. Okay.
I'm Bob Sutor. I was with IBM for 39 freaking years. And that's where I first met Bob Sorensen. He was an analyst. I was involved in various things. The last 10 years, I headed the mathematical sciences department and was also VP in IBM Quantum. Right now, I'm independent. I'm an advisor. I'm a consultant. I'm an author. I'm a kibitzer with a Q, of course. I'm just in the quantum industry. And my goal is I want to see this stuff really work while I'm young enough to understand it. Okay. It's always been 10 years, 5 to 7, 3 to 5, 15 to 30. And then it went back. Let's get all the pieces together to actually make a quantum computer that does what we expect it to do.
Thanks. Good.
Ooh, okay, we got a crab emoji there. I didn't expect that.
Oh my gosh.
A lot of thumbs up. Only one crab.
I hope that's not a diagnosis. So my name is Bob Sorensen. I'm an analyst here at Hyperion Research. I spent about, 35 years working for the federal government, where I was an HPC technology and policy analyst. So in some sense, my first love in the sector is looking at policy, whether it be U.S. centric or global, in terms of the challenges and opportunities of the advanced computing sector, which is so impinged upon heavily by policy, whether it be through funding, export controls, research programs and such. You can't separate the impact government has on advanced computing sector. By the way, Jay, I want to congratulate you on naming this advanced computing as opposed to HPC. I think advanced computing so much more accurately captures the nature of what the world is like out there. I used to say when I started doing all this stuff, you had to answer one question as an analyst: do I buy a Cray or not? And now there are just so many opportunities. There's so many different options out there. Am I doing mod sim on a classical CPU only? Am I getting into GPUs? Do I do on-prem? Do I do on cloud? Do I do a mix? Am I going to go into quantum? Am I looking at alternate architectures? I'm talking to a company, and this kind of really makes me excited. They're looking at an analog system where they are exploring reasonable accuracy on 16-bit floating point operations on an analog system. So there's so many different elements right now in advanced computing that offer opportunities if you get it right, and offer significant pain and suffering if you make the wrong selection. So this has been a time now where there has never been more choices to make in the world, and quantum is now moving forward to become transitioning from just being an interesting scientific and somewhat academic exercise to something that end users in the advanced computing ecosystem can now start to say, we need to start kicking the tires. We need to start understanding challenges and opportunities. It is coming. It's no longer an academic exercise. It is a reality that we have to deal with. Timelines could be argued, but eventually decisions are going to have to be made. Opportunities are going to be realized, and the world is going to have to think about where quantum fits into the overall advanced computing environment.
Well, I appreciate your kudos on the naming of this. I actually got a head start on it. I named it the Texas Advanced Computing Center when I started it in 2001. So I've always felt it should be more than just the high performance computing systems for numerical computation, large data systems, large remote visualization capabilities. At the time, grid computing was very big. And quantum computing fits into this broad sense of advanced computing. So I'm super happy to have both of you here. And that leads me into the first question, which this one I showed you ahead of time. I just want you to give a real quick summary of your feeling about the state of quantum hardware, software, research, and services, and just a one-liner on each and where you think it is, or maybe even a numerical score, 1 to 5, where you think each of those areas are before we get into more specific questions. So quantum hardware, let's start with that one. One-liner or a one-number score?
Ignore the spikes, ignore the hype, but across the industry, we're making steady progress.
Love it.
So everything's rising, but the claims of, wow, just ignore those.
I'm just in awe of the degree of innovation that's going on out there. There's so many different modalities, different versions within modalities. No one knows who's going to win. And the thing I find most intriguing is for all the different modalities, their various strengths and weaknesses at some level seem to be relatively balanced out. I don't think that there's a clear winner right now at the hardware level. And maybe there will never be a clear winner. Maybe we won't have the CMOS version of a quantum qubit for a number of years. Who knows? But it's the innovation. Every day it seems like someone's saying, hey, did you hear about this new hardware development? It's like, wow, no, that's cool. Can't keep the excitement there.
I want to make one thing clear here for those. That's what I've reached over. Let me also add, Bob, I track these. I know of 84 companies building quantum computing hardware, qubits, 84. Tremendous innovation, a lot of variety. No way in heck these are all going to survive, right? So focus, they're the big players and things like this, but focus on the individual achievements of them and what they're doing. And don't think of them so much as special to that company, but think of it as an improvement that if put together with the right other parts, because we'll see consolidation, we'll see other things, right? Will really give us a head start.
All right.
So I've been stealing that quote from Bob and giving him credit though. But the coda I add to that is if you take all of the traditional HPC vendors that have ever existed, from Seymour Cray working at CDC all the way up to today, I don't think the sum of that equals 84. So the depth and breadth of interest in this technology is huge, and much like what we used to see in the HPC space, when one company falters or trips, suddenly Thinking Machine is no more, Kendall Research is out of business. There was so much angst. We can't have that same degree of angst. There's going to be consolidation, but there's going to be organizations that are going to die on the vine. And we can't take that as a harbinger of issues with the sector writ large. There's got to be culling of the herd here. And hopefully the best will float to the top. But don't over exaggerate. Don't, any company that goes out, we're not going to have 84 companies competing in a decade. That's a non-starter concept.
It's also a very interesting industry. And Jay, I know we're talking more about your first topic, but
I really like these one-line answers, but they are very informative. So I haven't.
When you look at the companies, they're the big ones, right? There's IBM, there's Google, of course, Amazon, Microsoft, so forth. And then there is a cast of thousands, it seems, of startups. There's no middle, right? There are no companies of 10,000 people, right? It seems that are developing quantum computers. So since so many of them are startups, and typically 75 to 90% of startups fail, you will see that happen, right? Quantum people sometimes think they're a little extra special. They think they require a little extra time. They're deep tech. Investors do not believe that, though, right? And one of the most important things I will say for people as you look at all of these topics is, yes, you may be interested in the technology, but turn it around and look at it from an investor perspective and what they care about. That's part of the entire picture of the industry. It's not just about great qubits or networking or things like this. The survival we're talking about comes down to money in the long run. Are you getting it? Are you making it? Can you survive? because if you can't, you're just out, right? Good companies have gone away just because they ran out of money.
That is, I love that insight. In fact, that's insight for my question number 5 later in this interview. So I'm going to move to question 1B now and ask you to characterize what you think the state of the software is right now in quantum, and what your sort of 1 or 2 line assessment of that, and critical, constructive, satisfied.
I'll go first on this one. Yeah, I want to see more end uses. I want to see more applications. I want to see more use cases. It'd be great to have a killer app, something that everyone can really get behind. And to me, and I've been saying this, I've been using this kind of line of reasoning for the last couple of months, and I haven't been challenged by anybody yet, which is more and more I hear people buy NVIDIA GPUs not because they like the GPUs, but they like the software. And that's the justification. And I think that what we're going to see is much more interest, and the winners and losers are going to be defined more by their software capabilities than they will be by their hardware. Being able to access the right computational capabilities for the jobs that matter, and perhaps most importantly, being able to integrate that capability into an existing classical ecosystem is what's going to carry the day. It's not going to be whose T1 and T2 time is better. So I think I'd like to see a little more emphasis on what's going on in software development. I'd like to see perhaps a little more rigor, and maybe this is a role the government can play, a little more rigor in algorithm exploration. I'm tired of seeing kind of the same, oh yeah, we have Shor's algorithm, we have Grover's algorithm, and others. Let's have a more formal program where people are looking at this problem from an algorithmic perspective and then driving those into interesting applications and use cases. That's what's going to define, that's what's going to make this sector fly. It's not going to be a 1,000,000-qubit system where you ship it off and you say to the customer, go program it now. We didn't really pay too much attention to that.
Software, of course, there's more than one type of software involved in quantum, but also classically. At the very highest level, we can break this down into the tools, the tool chain, what you actually use to create something that will run on the computer of your choice, and then what happens at runtime, right? And that's usually referred to as a stack, from the lowest level, closest to the hardware, all the way up to the applications. And there are people who are playing in all aspects of this, and they all have histories, repeated history. So, for example, if there is a tool that is really handy for developers, but it's proprietary, you can count on there being an open source version that comes along, right? Because they'll write it themselves. So you have to kind of look at proprietary software and how long it has to live, basically, before it goes open source. On the other front, at the very bottom, you have lots of people who are doing like characterization, right? How well are your devices performing and things like this. A lot of those will probably be absorbed into the basic toolkits from the hardware providers themselves. They may exist as separate companies now. IBM, for example, does a lot of it themselves, as do other companies, right? Now, on the application side, and I have a report coming out on this too. I currently at 109 companies doing software with, by the way, over 450 different investors. So the quantum industry is getting worldwide, a lot of people throwing money into this. It's not just the big names. The two problems with algorithms, this fundamental question of how many really distinct algorithms are there? So if you talk about some of the NIST algorithms like VQE, there's a big thing with a funny name called an ansatz that sits in the middle of it and somehow characterizes the specific problem you want to deal with. Well, you're not creating an entirely new algorithm. You're just creating that new module in the middle, right? How long will that have to live? How well are you actually doing this? I have found on the application front, everybody and his brother and sister and dog and cat claim to do applications. And it's not really clear. And oftentimes they say they're doing hybrid classical quantum things. And some of these, I suspect they've thought real hard about the quantum part, and that's the extent of the amount that's actually in there, right? So I do think it's shaping up a little bit. I think there's a little bit less there than meets the eye now, right? I would focus, as always, on fintech, right? I think that's very well documented. I think there's a tremendous amount of information. Major question is, will we need error-corrected qubits, fault tolerance to do interesting things? And by far, the most overhyped is quantum for AI. Good luck figuring out when that will really be useful versus, being a marketing tool.
Where's my clap button here? Can I click that? Yeah.
So I asked you about hardware and software. So I'm going to ask about sort of the third component of this from an industrial perspective, the services sector. Often services is huge at the beginning of disruptive technologies, and then people begin to, build in-house skills or use software as a services packages where the expertise gets fully encoded in software. But we're in the early days of quantum. Are we seeing a strong services play here for companies that are exploring quantum, or is it even too early? Is the expertise too limited for much of a services play?
I haven't seen much of what I consider to be a terribly savvy service sector just yet. I don't think there's enough people within the sector right now to isolate, to fill that part of the ecosystem. And the ecosystem is filling out. I was at a presentation up at IBM last year where I think they had 6 different folks who came in with optimizing quantum transpilers, 6 different companies that were looking at that. So there are parts of the ecosystem that are being addressed. I think right now the service aspect of it, I just don't think there's enough people out there going around to do this. And I also think it's a really important aspect to fill out, because most quantum computing companies right now are too small, not sophisticated enough in the marketing sense that they can go and market their products to an oil and gas company on Monday, go talk to some pharmaceutical folks on Tuesday, go talk to fintech folks on Wednesday, with any degree of confidence that they're speaking the same language. And so at a minimum, the sectors, the vendors or the professional service organizations need to really start thinking about vendor or sector specific languages, use cases, and basically arguments about why they can work in those different kinds of verticals. But if you're just offering machine writ large, here you go, it's going to work, it's going to do all these great things for everybody, that's not going to make anybody comfortable when it comes down to writing a rather large check. And so hopefully the professional services sectors will step in with vertical specific knowledge as opposed to technology specific knowledge.
Yeah, I think there's fairly active programs by a number of companies, IBM, Amazon, Microsoft, just like, how do you become quantum ready, right? So it's education. It's saying you're a company in this particular industry. Eventually, how will quantum be useful for you? How will you, what steps should you take right now to do this, given the so forth? One of the problems with there not being applications in production is you don't have a lot of the major services companies stepping in to help you make production ready applications, right? Now, going a little bit more on the quantum ready side, though, if you are very serious about it, and usually it's some branch of your company called research, and to the degree that they're not all doing AI, right, for the company, they may need a little expert help, right? So we talked about algorithms before. There are companies, Phasecraft, for example, in the UK comes to mind, really deep expertise on getting the most out of what you're doing with algorithms. But as Bob said, you need industry expertise. You can't fake it talking to oil and gas and chemists and things like this. You can't be somebody who never did this stuff and think that you're going to have a universal solution for all these people. You're going to be laughed out of the room. Well, maybe they'll be polite, but once you leave, they'll laugh, right? And things like this. So there's a bit to it. There is a lot of very public information available, I must say. This whole quantum readiness aspect. I know there's one coming up really soon. I think the QEDC is doing one. That's generally a great way of finding information for a member or not a member. So if you need expert help, it's there. You can find it, but it's not what you might go to an IBM Global Services or whatever they're called now, Accenture, KPMG, the big guys. They're not doing that much, and there's not that much to do. But finally, let me just say, if you want the word quantum in it, what they are doing a lot for is quantum and security. Bob, you and I were both at a meeting actually 2 months ago where there were some banks who said, if you look at the amount of money spent in our bank on things called quantum, 25% of that money is offense. That is, how will quantum computing be useful? And 75% of it was about security, post-quantum cryptography, quantum key distribution, and things like that. There are plenty of people and services who can help you on that. But that's a cryptography story, less a quantum story.
Exactly. Yeah, there's more money involved in the near term there, and it's ultimately not a quantum story in some sense. It's, to me, I would look at that. I look at Shor's algorithm as the equivalent of saying the federal government has just decreed public-private encryption is no longer valid, and so you need to come up with an alternate scenario that doesn't factor a big number, and that's it. And so all of that extra stuff is quantum driven, but not quantum based in some sense.
I had somebody who actually, a very smart person who was just tracking this, but not an expert, who thought you needed a quantum computer to do post-quantum cryptography. So there's still some work to be done, but no, it's really on the cybersecurity side entirely. Quantum is just the potential threat.
Right, and so when people ask me about the whole issue of quantum security, I say, look, there's going to be post-quantum encryption algorithms that work. I think we're smart enough to do that. To me, the issue is more about deployment, and it's your point about the fintech stuff. I always point to the example for years upon years. If you went up to a VAX 11780 and you typed in your user ID was user and your password was password, you could get into about 95% of the VAX 11780s that have been deployed because people just never got rid of that user. It's all about operational security. It's not about post-quantum encryption that I think should be keeping people up at night. It probably takes 10 to 15 years to reasonably deploy a secure, invisible, and user non-intrusive encryption capability. The quantum stuff, as you said, Bob, it's not about quantum computers. It's about moving to a new encryption regime. That's the hard part.
All right, I'm going to move on to the next question here. I want to ask you for your thoughts, your confidence level that we'll be able to get to 1 million good qubits. And I'll let you define 1 million good qubits the way you want, but I come across people who think that we'll never get to 1 million good qubits. Others that think that, yes, we'll get there eventually, but we'll learn ways to deal with not so great qubits at the million scale level. People who think that we'll never get to multiple nines of reliability, and some that think we will. I'd like you to sort of address those two things. Do you think we will get to 1 million good qubits someday with as hard as this engineering is? And do you think that we will ever have even 1 9 of reliability in this, or will these quantum systems be sort of analogous to rockets compared to planes? Planes have multiple 9s of reliability. They just do the job. They move people and cargo, et cetera, et cetera, et cetera. Rockets do a specialized job, and they do it very well, things that planes can't do, but sometimes they need to be reset, I guess is the way we'll call it. So what are your views on that? Getting to 1 million good qubits and getting to 1 or more 9s of reliability. Does quantum computing lend itself to achieving either one of those goals?
First, on this million, you had PsiQuantum several years ago talking about they would deliver 1 million qubits at some indefinite point in the future. And people gave them hundreds of millions of dollars and continue to do so. Several vendors in the last few months have talked about whatever they did opened a clear path to 1 million qubits, right? So that number is just kind of used as a conveniently large number and much larger than what we've got right now, as opposed to saying, 1,475,000. Right, something like that. It's just classically big. For a long time, it was more or less thought that this would be some sort of threshold where we could truly do interesting things. Now, I might say that way back in 2017, we thought that number was 50. Just to be clear, we thought 50 was the magic number. Now it's much bigger. In the quantum industry, we have cleverly decided to call at least 2 different things qubits. the qubits that you implement in the hardware or use, be them Josephson junctions and superconducting ones, quantum dots, or ions, which you trap, or neutral atoms, and whatever they may be, photons. These are physical qubits, right? So there's somehow you can point to something physical, and that's a qubit. These are the ones that have varying degrees of errors. There's a very nice article that just came out about Oxford University professors creating one really great with a phenomenal error properties, right? Now, one is a long way from a million, right? You can kind of see what people are doing. We'll only be able to get so far, probably, in terms of most of these modalities, the types of building qubits, in terms of the errors, right? Errors are going to be introduced by just when we use them, by the environment. They're just going to degrade a little bit at times. Every time we tell them to do something, maybe there's a little bit of an error. Think of an example. If I do 5 plus 5 and I get 9.99 instead of 10, that's maybe an analogy there. So what do? Okay, well, typically you have, classically, we can detect errors and we can correct errors. That is in your phones, in your laptops. We do that all the time, right? Little bits, they might flip for some dumb reason. We can fix that. We need to do this in quantum. You can do it by adding a lot more qubits and a whole bunch of software and a whole lot of math, right? To somehow get this redundancy to improve the error rate. You're making a virtual or logical qubit. And those are the ones that will have the low enough error rate, such as 1 in a million, 1 in 10 million, things like that. But they're much more complicated to make. And by the way, you need more qubits to make, right? How many? Estimates of those vary from 1 qubit to 1,000 to maybe even 2,000 physical qubits to make 1 logical qubit. So you see lots of claims about how many of those you need. There's an interesting result announced last week by Nord Quantique in Quebec, which actually, when you get inside the qubits, instead of worrying about multiple qubits on the outside to give you 1 logical qubits, can you go inside the physics, inside a single qubit, and have this multiplicity inside a single qubit, so that to the outside world, the error rate's much lower. So I turning it inside out, right, to do this. So this is absolutely an area where there's phenomenal science and engineering going on. When you want to talk about engineering, this is what's going to happen. So will it happen? Yeah, I'm pretty confident that we will get to 1 million physical qubits. I think, to be interesting, we need about 100,000 logical qubits. And really, as we start doing larger and larger problems, that number will go up to, 1,000 logical qubits. Yeah, I'd like 100,000, but 1,000 logical qubits. And I think we're going to need 5,000 and so forth. It'll get there, but it's going to be a slow ramp. There's not going to be overnight, shooting up.
And do you think that those systems will have a reliability measured with even 1.9, or do you think that just the nature?
Oh, yeah.
Okay.
Yeah. I mean, physical qubits today have that. Mm-hmm. I mean, most of them are 2 and even 3. Getting below 3 is a challenge for physical.
At small scales, yes, but also the scale problem for mean time between failures for the largest classical supercomputers goes way down. Doesn't mean it brings the whole system down. True.
Well,
so it depends on how you measure the 9s, but gotcha. I think that's
also, I mean, so I'm on the board of New Quantum, which is a quantum networking company. There's my caveat. We're going to make big computers from little computers, and we're going to network them together. So we can get those fidelities in nice shape for the individual ones. But then if we're connecting them, we have to have low error rates on the networking, which is another question too. Gotcha. So yeah, it becomes a little bit more, it's more of a multidimensional question than just these qubits in one device.
Bob, any quick thoughts on this one about manufacturability of million good qubit systems, logical qubits, or however you want to define it, and reliability of such systems, and whether we should have the same expectations as we do for classical systems?
Well, first off, a million's a number because we name it. 10 to the 6th is what we named it. We used to say in school that you could always tell a physicist from an engineer. We look at 20 times 10 to the 6th. They look at 20 times 10. They look at 2 times 10 to the 7th. We like to keep things in 3s because they have names. So there's nothing magical about million. And in fact, I don't think I've seen a rigorous analysis that says, if I have 999,999 qubits, I can't do this. Give me one more qubit and now the world's my oyster. So that's just a marketing thing. The thing that I find pernicious about that is I don't want qubit counts to become the linpack of quantum, which means that this is the sine qua non of what we're driving towards. Are we talking about quality qubits? Are we talking about network qubits? What kind of capabilities are engendered by those qubits? So it's not just give me a million things that maybe don't have the topology from an interconnect scheme to do anything useful. So don't hang it all on a single number like we've done with LINPACK and theoretical peak performance and stuff. It's a much more richer environment that we need to somehow characterize here, as opposed to a single number. I think that the reliability issue is something that I think once we start to move away from, as I said earlier, kind of a research activity into a production environment, I think we're going to see more and more innovation when it comes to creating a system that appears to be very, very reliable. And one of my favorite examples of this is the DRAM. The DRAM can be considered as nothing more than a bucket with a switch that allows electrons to flow in and out of it. Well, that bucket is so leaky that you have to refill that bucket on average of thousands of times a second. That's how leaky it is. So the DRAM, which is 10 to the minus 18th error rates, is one of the most unreliable concepts that you could ever field from a production environment, except it has a really, really elegant solution to error correct.
Yeah.
And I hope that when engineers and product people start to look at quantum, they can think of additional clever ways, at either heuristically or production-wise or even in a usage pattern, to say we can beat some of these issues down the road in a production-level capability. So I'm hoping that the engineers step in and really start to make this a product as opposed to a research activity, and I'm very optimistic about that.
I want to just qualify some of my numbers before, because I think I got lost in the zeros and the exponents a little bit. I think the threshold where we will start to get interesting things are 100,000 good physical qubits to get 100 really good logical qubits. Those are the numbers that I'm talking about. Okay. And yes, it's my really good qualifications that say it's not just the count of qubits, they have to have other characteristics.
Right.
But it's with 100. I gave this old example about a caffeine molecule, right? And here we're talking about perfect qubits. And in the example, it's, I believe it went something like, if you were to assign, if you wanted to fully represent the electronic state of a single caffeine molecule, the number of atoms you would need, number of bits you would need, zeros and ones, would be between 1 and 10% of the number of atoms in the Earth, right? You can't possibly having so much memory as that. But if you had 169 perfect qubits, you could represent it exactly. So that gives you a scale, but it also says if you're starting to get serious about chemistry, right, that's about the threshold that you want to go. If you're now talking about antivirals and things like this, add another 0 or 2.
All right, we've got time for probably 2 more questions, and I have a half dozen. So I'm going to pick
not the way
2.
we answer it, Jay,
Yeah.
just to be clear.
Yes.
Maybe half a question.
We could go like Jeopardy if you gave us a buzzer. And we could.
You guys are so fascinating and such experts in this that I'm going to poll the audience here real quick. I'm not going to poll them on which questions because that would take a while. But would people want to tune in for a part 2 of this? If you'd be interested in tuning in for a part 2 of this, yes, the sparkle heart emoji or the thumbs up or the, if you would not, you can use the crab, but I hope I don't see any crabs. Any of the other meat emojis work pretty well there. All right, so Bob, I'm going to try to schedule you for part 2 of this. I'm going to close this with 2 questions that I think speak to the applicability and importance of this, and then something practical for folks to take away. The potential impact is huge here, right? We've talked a lot about viability of building these machines, feasibility of these machines. You've even gotten into some of the aspects of feasibility of companies in the sector. But the state of algorithms, you both alluded to it before, but there's still not a large number of algorithms that have been shown to not just theoretically have a quantum advantage point like Grover's or Shor's, but have a quantum advantage at a practical problem scale. Some really interesting problems. I'll discount quantum simulation of nature for a second, the Feynman's, argument theoretically for quantum systems overall, but I don't see outside of that, I don't see a lot of algorithms yet that at practical problem sizes, people are highly confident that quantum will be the way to go. Some, yes, not many. Argue with me on that statement. What are you seeing in terms of quantum algorithmic research, and are you sort of the Scott Aronson school of thought where there's not a lot of these algorithms yet, or are you more optimistic that there will be a lot more once people get hands on these systems and have had a few more years to think about quantum as opposed to classical algorithms?
Let me jump in real quick. I like to point out that there's reasonable evidence that Chinese mathematicians were using Gaussian elimination BCE time. Navier met Stokes in the 1820s. We have a vast amount of experience in algorithmic mathematical development in the classical world. Shor's algorithms turns 30 this year. Unlike the Who, we have to trust something over 30 here. But the bottom line is we need to give quantum some time. It's a vastly more complex mathematical regime. A lot of the algorithms are not intuitively obvious. I can explain a depth first versus a breadth first search rather trivially. I can explain what's going on in a quantum fast Fourier transform, the heart of Shor's algorithm. So I think we're being unfair in terms of expecting the hardware and the software and the algorithms and the use cases to all evolve in parallel when the classical world had 100 years to do that. So to me, I'm saying give it a little time, give it a little patience. Like I said, these things do take time. But once you start to get systems in the hands of clever people, I expect new use cases from existing algorithms and some interesting innovation in new algorithms, just because there's going to be an untold number of folks who are going to be trying to solve interesting problems and are going to try to figure out a way to get quantum to help them along that path.
So quantum is not a total replacement for every hard problem we can do classically. There are generally, from a theoretical computer science perspective, three classes of problems that fall into these things that we think quantum will be useful. So whereas you have general computing, and then tons of algorithms. I mean, how many sort algorithms are there, right? Just for example, but people don't use them all. We're really focusing on those three, and really coming up soon is the simulation of physical systems. I mean, those are going to be the first winners, right? So we don't want to ignore those. That's where we're going to see it. There's always the question of whether we'll have to wait for these logical qubits with fault tolerance and error correction and scaling, as we talked about before. To what degree are the so-called NISQ algorithms, variational algorithms, are they just, placeholders for now? They seem, because people want quantum computers to do something good and useful right now and not just wait till eventually we do that. So there is this kind of flux going on, like, oh, I'm developing this new algorithm, I'm developing a new ansatz, but in 10 years, will anybody possibly do it that way? So yes, I very much agree. Once people get their hands on powerful enough real quantum computers with error correction, it will drive a lot of this new work. Many of the early algorithms were proofs of concept, right? There are a lot of the famous ones that are, like in my book and other books, Deutsch Josa, you'd never use for anything practically, but it's the most famous algorithm, right?
Yeah.
Another thing about Shor's algorithm, right? People love to talk about hybrid quantum classical, which I really dislike because you can't run on a computer without classical, right? Shor's algorithm, 2/3 of it is classical, 1/3 is quantum, right? So think of them together. Don't think of just quantum algorithms. Think about how quantum can augment certain parts of larger algorithmic schemes. They don't have to do everything. And that's where I think the richness and how it will eventually play.
Bob, that's a really good point. And by the way, Bob Sorensen, I totally agree with you. It would just, when I'm talking to friends, it would make my life easier if I had a longer list of algorithms that had been proven to have to be proven to have a quantum advantage at a reasonable number of qubits for real world problems. But I totally agree with what you were saying about timescales, giving it time, et cetera. The amount of time we've been looking for quantum algorithms is very small. Bob Sutor, you just said something really interesting that I might adopt into my phrasing from now on, which is the phrase hybrid classical quantum computing has been out there to describe these systems to sort of emphasize to people that they will not be using strictly a quantum system. But maybe that phrasing in trying to be overly explicit is just redundant. Maybe just the term quantum computing should be thought of course, it's a hybrid classical, it's a quantum accelerated system. It's not you're not using a quantum system for a real problem. You're using a quantum accelerated system for a real problem.
If you think of an entire AI workflow, right? So the data, how much of that actually involves a GPU, right?
Yeah.
There's certain designated portions of it, but not everything. A lot of the data handling and things like this is just classical and lots of variations. So yeah, whether it's a component or an accelerator or whatever, it's just part of the computational toolkit. And that's where I think people will get clever. They're not going to be full blown, but they're going to be refining certain parameters that might be used later on in something else.
One of the issues I have with some of the rigor in the whole algorithm exploration is the idea that in the classical HPC world, if you can give me an order of magnitude performance improvements on my most critical workloads, I'm really happy. That's a great thing. And yet people say, oh, Grover's algorithm, it just moves from order n to order n squared, big deal. Well, I imagine there's an awful lot of people out there who would love to move from order n to n square root of n, excuse me. And so I don't understand. If I went to an organization and said, I could give you 100x performance improvement, they're going to go, oh no, we don't want that. I've got to have intractable quantum superiority, or I'm not interested. So I think that there should be a certain amount of reality on this, that a classic HPC site that can get an order of magnitude performance improvement that gives them perhaps a significant advantage against a non-quantum counterpart in the marketplace is not going to be ignored. And so I think we're being a little too strict when we look at some of these speed up potentials that could offer some significant competitive advantage, even though they may not give you exponential speed up. They may push you down the road 5 or 10 years what you get if you stayed in a classical compute environment.
Well said.
An order of magnitude improvement is a linear improvement. You're multiplying by a number, 10.
Right.
Then we get quadratic, square roots. Then we get exponential, which are logarithms and things like this. So each gets better, but the latter two only truly get better for very large problems.
Very large numbers, exactly.
And that's the other thing, is we don't need quantum to solve little problems, right? There's a threshold where the problem gets too big for classical, that's where quantum. But we can't deal with very large problems yet in quantum computers. So we get indicators. We say, this is probably a good path, and things like that. So once again, when we can, maybe there'll be even greater algorithmic innovation, right? Or maybe, the problem is still ultimately intractable for arbitrarily large problems, but we can now deal with much bigger problems than we could before, right? So if it helps, it's good. The more it helps, the better.
Yeah. All right. Lots of great questions left, but we have 9 minutes left, and I've got 2 minutes of announcements to make. So I think we've already agreed. I'm going to beg you two guys to come back for a part 2, and we're going to label this part 1 when we post this video, and we'll schedule a part 2 based on your availability, of course. But I do want to take some audience questions to close this out, because I see several good ones in here. I'm going to ask this one from Joshua Williams first. I am joining as a quantum computing enthusiast, so please bear with me. Aside from qubit count, which performance metric, quantum volume, error rate, or circuit depth, best indicates a device is ready to use, and why?
I'll let you vote, Bob.
Well, quickly, we had a session at one of our conferences at the quantum on quantum, and we had about 5 or 6 different quantum companies, and I went down. I asked literally that very question, and everyone had an interesting, sophisticated answer. And a gentleman, Yuval Bulger, who's a kind of a interesting character, a company called Quera. He said, here's our benchmark. We walk in and we say, what's your hardest problem that we can solve? And he said, that's the benchmark that matters most. And so to me, it's if you want to characterize hardware, good for you. But the end user is not going to make a difference in that. And my answer to that is, when was the last time you bought a server and you said, are you using FinFET or gate-all-around transistor technology in the CMOS transistors you're using? No one asked that question. So to me, if you want to look at the hardware, that's a really great thing, but I'm just going to say it again and again, look at the use case capabilities of a system, not its T1 or its T2 time, because I can almost guarantee, and we call it the VHS beta syndrome, the best technology doesn't always win. There are a multitude of factors that engender market superiority, and it's not going to be who's got the best quantum volume. It's going to be who offers the best solutions.
I mean, but to be fair, Bob Sorensen, sorry, I'm going to interrupt for a second. Each of those things does correspond in some ways. There are analogs from the classical world of HPC to whether a system has more processors or better network connectivity or more uptime or things like that. So those weren't all measures of, those weren't all questions about the physical nature of the modalities, but they were around the size, the connectivity, and the durability of the system.
Okay, then the answer is whoever scales the best. Whoever can scale in a nice modular way to get to a problem, and who can beat the I/O problem.
Quantum volume is no longer useful. Hasn't been useful for quite a while. Quantinuum recently maxed out the best you can do because you need to be able to simulate some things classically. So that's done. Nobody. Assuming you have a lot of really great qubits, the second most important thing is circuit depth. I have to be able to run a lot of instructions, like millions of instructions, not 100, not 1,000, millions of instructions. So in fact, however many qubits you have, think of 1 or 2 orders of magnitude more circuit depth you need, right, to do interesting things in the long run. So that's my vote. But again, has to be good, has to be high fidelity, things like that.
All right, let's see. I'm going to ask a question now by Shenglong Wang. There are different hardware for quantum computing. For the application software and methodologies, are they compatible with each other? So I think this question is getting around, can you run quantum software and applications on different hardware modalities?
Hardware agnostic?
I think that's what this question is, yes.
Okay.
There are 3 paradigms. Annealing, which is done by D-Wave and a little bit by NEC. The rest of the world is made up of analog and digital. Digital is 75% of the total, all right? That's gates and circuits. That's fairly general on the top. You can write backends for those for things like Qiskit and CERT. However, one of the problems with one size fits all from software development is you can get software that runs badly everywhere, right? So you must have some little place there in the middle that optimizes some intermediate form for your particular hardware to run well, right? An intermediate representation and IR. There are specialist people who do that. So at a high level, yeah, we'll be able to do more of it as long as there's a very good low-level optimization compilation code layer.
This is a classical. The HPC world's seen it for decades. Every time a new architecture comes out that looks hard to program, they say, "Oh, we'll let the compiler writers deal with it," and that's what's going to happen eventually. That no general purpose hardware agnostic component is optimized for whatever you're running on. We'll let the compiler guys deal with that as well.
Well,
and look at how successful that's been.
When I first heard about big endian and little endian, right, for example, it's like, you got to be kidding.
Yep.
I shouldn't agree on this, right? Anyway.
All right, so we're going to do one more quick one. I'm going to ask for a truly quick answer to this so I can get to the final slides and let people go at the top of the hour. Kostas Pekas asks, could you comment on the complexity of data input? I may not have picked a very quick question. It is perhaps where complexity is now hidden with respect to the QC. Is it perhaps where complexity is now hidden with respect to the QC paradigm?
I love this question because in general, taking classical information and quantum encoding it, and there are many schemes, right, is exponentially expensive in terms of memory or time or things like this. So many of the people who talk about quantum for AI and their amazing middle part ignore step one, which is virtually impossible. So if you ignore the impossible part that you have to do first, my code is great, you know, and things like this. So many of these algorithms, including Grover, are only important if you're starting with quantumly encoded information, right? So you may get that. You may get it from sensors, right? You may have it coming over a network, right? Things like this. You may get it as a result of a previous compilation. But yes, it's a huge, huge problem. So therefore, if you ever read about, oh, I've got petabytes of data, thank goodness quantum computers are coming along, right? Stop reading. Go away. They don't know what they're talking about.
To me, I just like the paradigm. GPUs, they're all IO centric, and the processing that goes on in the middle is relatively trivial. I mean, for most of the GPU applications, quantum is the exact opposite. Incredibly complex computational capability in the quantum realm, absolutely minimum capabilities when it comes to IO. They are diametrically opposed. They are wonderfully complementary at some level. But don't, you know what Bob said, don't delude yourself. This is why both of us, I think, are one of the most violent skeptics when it comes to AI. I don't know how you deal with handling large quantities of data in an environment that doesn't like large volumes of data.
So I'm going to get to the quantum and AI one in the part 2 of this. I didn't get a chance to get to it today. I look forward to addressing that. And I'm going to throw some interesting counter arguments to where I think you both stand that you can then slap down in part 2. I want to hear your counterpoints to those as well, because I think that's an area of great interest, quantum and AI together. But with that, I will say thank you both I really appreciate you both giving us this time and being so flexible, rescheduling this when we had the technical issues last week. I hope I can talk you into doing this again. We had a large crowd, and I'm sure a lot more people will tune into this on YouTube. We've got a lot of applause happening right now with the Meet emojis, which is probably my favorite feature of Google Meet, actually, for the audience to be able to actually share their appreciation as well.